Okay, so it's a great pleasure for me to introduce Abhinay Belde. So Abhinay is a master in computer science from here Purdue University Fort Wayne. He graduated this spring, and he done some very nice work on I-JEPA. In particular, he extended the original algorithm through a combination of diffusion models and generative adversarial networks techniques with application to medical imaging. I had the pleasure to serve in his thesis committee, and I was able to observe his great analysis, his great skills. So it's a great pleasure for me to have him in the seminar series today. So, Abhinay, please go ahead with your presentation.
Thank you, Professor, for the introduction. So I'll start my presentation. So it's basically called, so it's the PPT is titled as Beyond Representation Sampling. It's an I-JEPA conditioned diffusion GANs for medical imaging. So, so I would like to give us a brief overview about how we're going with this. So I'll be giving out my motivation, the problem statement, contributions, and then I was thinking that I could give a small background so that we could understand the methodology and frameworks better. And I'll finally discuss about the results, limitations, and future work. So, coming to the problem statement, what we realize is that there is a scarcity in data sets. So now, and also when it comes to generative AI models in medical imaging, we see that the images are very complicated, and then there are not much models that actually work well when it comes to unsupervised synthesis. So what we came up with is we can use a diffusion GAN conditioned on an I-JEPA encoder to help with this. So the key contributions here are to inject frozen I-JEPA features into the style GAN and diffusion backbones. Um, and we propose a unified conditioning interface for the generator and the discriminators so that the embeddings flow through the entire architecture smoothly. We introduce some hyperparameters, which I will be showing in the later slides, such as the warm-up ramp schedule and depth mixing schedule for in basically to make the training more stable. We conduct the experiments through two medical data sets, which are essentially the chest X-ray data set and the brain MRI X-rays. And this code is available through my GitHub, and it's there are steps which you can reproduce, which you can follow to reproduce the results. I mean, so coming to the background, so we my motivation is to like use the architecture, which is the StyleGAN itself. So StyleGAN gives out a very good architecture where it has this 8-layer mapping. Um, so what it does is it takes a Z and then it passes it through the 8-layer MLP. So the key idea is that first of all, this is StyleGAN 2 ADA. So what this does is it introduces something called weight demodulation. So its predecessor, which is a StyleGAN 1, it introduced some artifacts like droplets, and so StyleGAN 2's motivation is to like remove those droplets and get a better realistic outputs. So, another thing that StyleGAN has introduced is to train images with full resolution rather than progressively growing the network. And also, this has introduced something called path length regularization and laser regularization that could actually help us maintain smooth latent traversals so that the gradients flow smoothly during training. And now coming to the 8-layer mapping network that I was initially talking about, that actually transforms the latent vector Z into intermediate layer style vectors W, which I take advantage of this to try to somehow inject the I-JEPA embeddings later on, which I'll show in the methodology. So moving on to the uh, next architecture which we've used was the projected GANs. So here it's a very smart thing to do. Here, what projected GAN paper or the authors in the projected GAN paper has done was, we see that in the traditional GAN, the discriminators are trained from scratch. What the authors have proposed here was to use a pre-trained backbone, which is like an efficient net or a dyno, to use the features from that. So there are two major effects that come with this. First is that it shifts the objective from matching pixel level distributions uh, to match the representation distributions. So it basic what I'm trying to say is it matches the semantic structures better. So this also allows us for better stabilization during training, since the pre-trained features are already encoded pre-trained features already knows how to encode meaningful visualizations for the images that we are training, and the GAN doesn't have to like learn from all the way from the start. And this actually has showed that the training can be sped up to about 5 to 10 times in speed, and also has shown better FID scores. Our concern is to have a stable training and to have a better fidelity. So we even explored hybrid architectures such as diffusion GANs. And the idea is to use a simple forward diffusion process that gradually adds noise to both the real and fake images. So this actually produces a range of distributions from almost clean to heavily corrupted samples. So what happens is, at each time step, suppose I can take it as t, at each time step t, the discriminator in this also, since it's a hybrid architecture, it has a discriminator and a generator. So the discriminator receives samples from a specific noise to signal ratio and must actually determine which um, from which it came from. So so this makes, so it has, this architecture has complete control if it can make the problem statement a little harder or easier. So what we observed is that the result is much smoother when it comes to adversarial training process. So since from the beginning, I've been talking about how to use I-JEPA embeddings into this architecture. So how it actually works is, it uses self-supervised learning technique. So they actually use three encoders, three VITs, which is basically a context VIT and a predictor and a target. So uh, if you take a complete image, what context encoder does is it takes a huge chunk of the image and it keeps that as a context. And as we see here, the predicted the target blocks, it could be some overlapping target blocks, which can be grouped into some boxes, and the predictor has to actually use the context and try to predict these target blocks which could be overlapping. Through this, it actually learns some meaningful representations, and it even can be used as pseudo labels further for conditioning generators. So one of the works that actually have done this is called as RCG, which is a representation conditioned which they call it as representation conditioned generation. So what they do is, so traditional diffusion models operate in pixel space, so which makes them good at capturing texture, but also not necessarily with meaning. So this RCG, right, this paper, this moves the generation process into semantic feature space. So what try to take a encoder, which is like which could be I-JEPA itself or any other encoder. They try to take that and they get a feature space. They try to take another diffusion model, which they try to learn the feature space, which is a representation distribution. Once they learn how the representation is distributed and how the data set are actually clustering each image, they use that information to condition the image generator, so that this noise so if they take a sample if they take a latent vector, or if they take completely try to denoise from an entirely what do you say, in diffusion models, basically they completely destroy the entire image and they try to denoise the uh, entire thing to get a final image. So they use this distribution which they try to model it from a diffusion model to condition it better. So coming to the methodology, I would like to just talk about the basic overview. So first, what we do is we do something like RCG itself, but we try to do something where we can inject the embeddings directly into the generator itself. So visually, what I would like to say is that we first pre-train a I-JEPA encoder. We try two things where we can use a CNN-based I-JEPA or a VIT-based I-JEPA. So our main concern was to address the issue where the data set is very small. So in that case, VITs would not do a great job. So we stuck with the CNN-based I-JEPA, and then we provide the features to the baselines, which is the generative backbones. And then once they are conditioned, we also see how the features are semantically good, and then we produce images and see how the image quality is based on FID and precision recall. So when it comes to the data sets and for the data sets, we used chest X-ray dataset and brain MRI. So here I just mentioned that in chest X-ray, we I think we used about 5,284 JPGs, and for brain cancer MRIs, we used 5,712, which is considerably very low when compared with other data sets, which could be around uh, 20,000 to 30,000 in each class itself. So here, it's pretty simple for chest X-ray, where it just uses two labels, but we wanted some other data set which has more than two labels, like such as brain cancer MRI data set, which uses four classes.
Abhinay, do you mind if I ask you a question?
Yeah,
So
sure.
you mentioned about using, these diffusion models or GANs type models at the representation level, so at hidden representation level, right?
Yeah.
So at which level? So the reason for which I'm asking is that, when you have hidden layers, maybe the first hidden layers can
Mhm.
you can kind of interpret them, right? Some take care of the boundaries of shapes and so on, right? So
Yeah.
maybe at that level, you don't need something very general, right? Because you just know that you need to figure it out the shapes, right? Somehow you have to figure it out something which you know what you have to figure it out. So
Hmm.
it's possible that you're gonna have an effect on. First of all, you're gonna have an effect on which layer you are trying to match.
Yeah.
Second, maybe that different presentation might better match different layers.
Mhm.
Um, but also maybe that in some situations you don't need something completely general, so not based on any assumption. Because in some situations you can input some understanding of what the layer is doing, right?
Yeah.
So how do you choose at which layer you do this representation matching?
Actually, in StyleGAN, we have this mapping layers which actually takes the Z latent vector, which is completely entangled. So the mapping layer basically tries to entangle it in such a way that we can interpret it and control it in a better way. So once it goes to the MLP layer, it distribute the styles go into each of those layers. So now we know that the initial layers control the global structure, and the later on layers control the final details. Since we just want to condition the generator in such a way that it can condition the classes better way, we what do we do? We just send this encodings from this I-JEPA to the initial layers, which is basically my methodology that I'll be showing in one or two slides. I hope I answered
Good.
that.
Yeah, thank you.
Yeah. So um, coming to that. So basically, about the methodology, I will shortly tell about how we inject the embeddings into the layers. So before that, I would like to just say about how the representation quality of this embeddings are. So here I'm showing how the pre-trained I-JEPA embeddings look when we projected the 2D space using PCA and TSNE. So the top row we have the chest X-ray dataset, and the bottom we have the brain MRI dataset. And in the PCA plot, you can already see some linear separation between the normal and the pneumonia class. The spread mainly happens along the first principal component, which likely captures global intensity or texture differences in mainly in lungs. I feel because it's a chest X-ray, right? So there is a bit overlap, which is expected, but overall it shows that the representation is linearly discriminative. But if I extended this to using Stiesny as well, which captures non-linear structure, uh, we can see clearly how the separation is seen, and the clusters are very compact, and samples belong to the same class are very close to each other. So so what happens is now for the brain, even for the brain MRI data set, we see that the PCA plot shows a smooth curved manifold that's actually trying to connect two to three, not two to three, the three tumor classes, but it is clearly able to separate out the non-tumor classes. So this actually tells us that the embeddings understand this shared structure across tumor types. And if we see the TSNE variation as well, the TSNE version, what I mean, uh, it's able to like distinct each classes clearly. So even in some cases it's trying to see if there are some subclasses inside some classes, which could sometimes be different types of tumors itself of the same group. So overall, we understand that the I-JEPA embeddings are able to like capture the classes in a just by pre-training them on the data sets. Oh. So for further training, for further testing, I've tried linear probing and 10 nearest neighbors accuracy as well. So here I saw that we were getting linear probing accuracy as 97% for both the data sets. So this kind of proves that it's matching what we've seen in PCA plots. So even what I thought was even a simple linear classifier can actually separate the classes fairly well, which means that embeddings are linearly separable. So the metrics are pretty um, clear to make me understand that I can go forward with this.
So at the same time, it might raise a question on is the representation too high dimensional? Maybe there is a lower level representation. Because of course, when you increase the dimension,
Mhm.
classes become separable. But there might be that is an even more parsimonious representation here, right? Which might be investigated further. Yeah,
Yep.
good.
So yeah, so this is a baseline. Yeah. So here what I'm saying is now for the baseline models and the training setup, we've used the the style GAN architecture itself, and the diffusion style GAN, and the diffusion projected fast GAN. Um, first, we have introduced some hyperparameters that could actually help with stable training. So firstly, it's a fusion depth K, which is the over here this fusion depth is 4. So initially there was a question where we asked where it was asked that how do we know which layers the embeddings are sent to. So here this actually controls how many style layers. So the style GAN was using about 8 MLP layers. So I won't here the fusion depth is like 4. So this the embeddings were only being sent to the first 4 layers. And then we have the fusion strength and alpha, uh, which is here. And yeah, fusion strength, I've named it as alpha in the code as well. So here what I thought was, this is learnable, and it controls how strong the embeddings influence the generator. I also introduced semantic ramp. So here I think I mentioned it as the warm up length. So here it gradually increases from 0 to 1 over the span of 5.8 k images. So the 5.0 k images as in 5,800 images, the number of times the model sees the images for one epoch. So the main idea is that instead of seeing the embeddings at the starting itself, where the noise is very chaotic, and the model doesn't know what it is generating. So if it somehow ramps up slowly, so that it slowly learns what the embeddings actually mean, is the idea behind this warm ups length itself. And then we also have the semantic mixing probability. This idea is actually borrowed from the style GAN itself, where they use something like style mixing. So we have used something similar to that, which is called as semantic mixing probability. So it kind of mixes the it says it what it says is that it determines how often the embeddings are injected into the generator. So I don't want it to like completely depend on the embeddings itself. So I made it like, so if it is zero point 0.7, it depends on the embeddings 70% of the time. I think I updated studies through zero point 0.6, zero point 0.5, and zero point 0.7 to see how the FID score changes. So to finally come to the I-JEPA fusion conditioning, this is the method that we actually introduce. So uh, starting with the generator, so we have the latent vector z, which is mapped through the usual 8 layer mapping network to produce the style vectors w. So they name the style vectors w. So in parallel, what I do is I project the I-JEPA embeddings, which is the for in this case I've decided to go with 1048 dimensional dimension for the embeddings itself. So then what I do is I compute a semantics shift by scaling the embedding with a learning strength parameter called alpha. So and it uses a semantic ramp that actually gradually increases during early training. So here we see that there's an I-JEPA embedding layer over here, where it goes into the MLP itself, and then it tries to use that style layers to somehow synthesize the network. And then we also use the same technique in the discriminator as well. So when it comes to the losses, I've mainly stuck onto the original losses that come with the style GAN itself, and then introduce a new semantic feature matcher, which is basically like cosine similarity. So here what it does is it takes the it takes the features from the real image and the fake images, and just checks the cosine similarity between the two, and sees so that it can match the features of the embeddings. There's another future work which we are actually considering, and it's still in development, which is to use the CCA loss. So here it's basically trying to see how to maximize the difference between the real and the fake encodings. That is something which I'll talk in a while. So finally, coming to the results here, uh, what we've observed was that in the experiment one, where we only use the cosine based I-JEPA loss, so we had like two experiments, which is the cosine based I-JEPA loss, and the second experiment is the fusion mechanism, where we use the I-JEPA loss as well as the fusing the embeddings into the network itself. So for the chest X-ray, which has the two classes, normal and pneumonia, the baseline already performs quite well, which is coming to about 5.6 FID. And even with the JEPA loss of fusion, the numbers almost remain the same, showing that the model already captures the low level variations between the two categories. In diffusion style GAN, we do see a little improvement, which actually reduced from 10.09 to 9.32. So, which is kind of good because we want a lower score. So, but the main um, what do you say? The main improvements that we've actually observed was in the brain MRI itself, where we see a 25% drop in FID score. Initially, the baselines are at 34. The style GAN was able to produce a FID of 34.88, and it dropped all the way to 26. That's pretty good improvement when it comes to showing that the I-JEPA embeddings can actually improve the networking conditioning. So this also means that the generator has some information where it can generate data in a better. Uh, it can actually generate more precise data, and it can also help in some diversity. So the key takeaways that I would say from here is that the semantic embedding signal matters because most of the as the class diversity increases, because in brain MRI we see that we have four classes and then chest has two. So as the number of classes increases, we see that the semantic signals that we are sending through the IJPA actually show some improvement.
So are the two sets of images of different quality, different resolution, stuff like that? So what's the
So so the both the so we made sure that the both the data sets come with the same resolution, which is 256 by 256, just so that we can see that there's a consistent synthesis between both the networks.
good? Good.
So yeah. Yeah, so in the previous results, we see that the projected GANs are also doing pretty good. One thing that we have observed was that when we compared the I-JEPA diffusion projected GAN, the convergence was like almost 8% faster, which started off from 16 itself, where the normal baseline started with 18. So we at the end it just ended up getting the same score, but we saw a better convergence, which could also say that it is somehow trying to boost the network to produce better images in a faster way. During experimentations, some things that we've observed was the training instability that we've been trying to address from the start. So initially, the thought was to use the I-JEPA embeddings only in the generator, where it can somehow guide while getting information from the discriminator. Well, that wasn't working. Where we only tried injecting the embeddings into the generator, and then the training just collapsed, as we can see through the graphs here. So one and then what we thought was, okay, maybe generator doesn't need the information, and then we only tried the discriminator only. The training somehow improved, but then at some point it just collapsed, and the FID started spiking. So what actually helped was to maintain a symmetric embedding injection, which is like to send embeddings through the generator and the discriminator, so that the generator doesn't cheat to somehow fool the discriminator. This actually helped to maintain the training stability, and then we were able to get a better FID scores compared to the baselines. So the main limitations that I would say with our method was to although we are improving the state of the art backbones, we are not this is not completely supervised unsupervised. The So initially, when I was talking about the semantic ramp and then trying to like warm up the models, we are actually having the information about the class labels. So that is something that I'm trying to solve, where I can use techniques from RCG, where I can model a diffusion model to understand the labels itself. So it is slightly supervised, but not completely supervised. And then we have this additional overhead where we have to I wouldn't say overhead, it's just a extra computation where we have to pre-train an I-JEPA, which I actually observed by just normally using I-JEPA without pre-training itself also worked pretty well. So the future works, which I'm strongly inclined towards, is going towards fully making this method unsupervised, and then also using techniques from object detection and segmentation, where models such as SAM and mask to former. So SAM is like pretty good. Segment anything model is pretty good with uh, like segmenting and like differentiating between objects in the scene or an image very good in a very good way. And master former is pretty good with giving some semantic meanings for the bounding boxes. So there is a idea where we can like somehow use these techniques to improve the semantic meanings using I-JEPA. So and also yeah, that's basically it. So any questions?
So let's thank Abhinay for the great presentation. So I have a question. Go back to the previous slide when you talk about class imbalance. So just the one preview before this one, maybe.
Sorry, the previously.
Yeah, the one before this one, I think. You talk about, yeah. So class imbalance. Okay, so if you just train logistic regression model, okay, and you have a class which is, your case, right? So rare tumor type or rare disease versus, healthy people. Then you have that the class is really unbalanced, right? Maybe there is a disease which happens one time over 1 million individuals. Okay,
Mhm.
so now if you train it with the standard logistic regression, namely with the threshold at 0.5,
Mhm.
then you're gonna always predict the healthy class. Now that parameter alpha there, though, can be chosen through data drivenly. So you can choose that parameter from data. Which makes the threshold for predicting one class instead of the other different. So it is possible that also in your algorithm, these class imbalance issues that you have
Mhm.
in the accuracy of the algorithm, it's because there are some parameters that you are not chosen through data. So I believe that some of the parameters there are parameters that have been chosen, because of problems with computational cost and so on. So you just fix them. But it's
Mhm.
possible that you're gonna fix this problem with accuracy by doing something data driven. And I think it's important because at the end, the doctor is gonna see a population which is the population is gonna see. And the classes, when disease is rare, they're gonna be imbalanced no matter what. So if this thing needs to be useful, it needs to work for doctor or prediction, it needs to work for imbalanced classes. So this is a very important problem that you are addressing there. So what are your thoughts about this?
Well, that's actually a very good question. And is so. Let me try to. So, are you trying to say that we are the hyperparameters that we are using in the generator? There, it could be that some of the parameters are actually tending towards some classes which are not addressed.
That's basically what I'm saying. So here it's a problem on the hyperparameters, and the hyperparameters are probably placed there for previous experience or whatever experimental decision, but they don't come out of cross validation procedure or variable selection procedure and so on. And so
Mhm.
those values there are not driven. And when you have imbalanced classes, usually there is that issue there. And
Mhm.
of course, if you have these really unbalanced classes, some standard algorithm, but also other algorithms, because the principle is the same, end up getting always the majority class. And so then you have a pure accuracy, and that's because of the upper parameter issue. So it's probably something that you can work on there.
Yeah, yeah, correct.
Very good, awesome, good, very good. So if there are no, yes, Jeff, Professor Anderson.
I didn't know if I should raise my hand. So I'm sorry if you hit this in some place and I missed it. The thing I'm wondering about is a couple of potential, if it was anything, having to do with these Gibbs artifacts that are part of MRI data? And actually, your diffusion edition may have something related to it, given that this whole artifact is due to just approximating diffusion solutions with a Fourier series. They get, 9% overshoots and undershoots.
Mhm.
So I guess a couple of things. One, do you know if the MRI images you have already been kind of cleaned for Gibbs images? I think
Um,
I think
yeah.
some of what you had were spine, specifically spine MRIs.
So the brain MRI images that I've used was the top level, the top view images,
Okay.
which mainly show there were certain views where I could see from the side and the back itself, but then most of the images, like at least 99% of the images were all top based images, top view images.
Okay. Because then the second, if I read your uh, procedures right,
Hmm.
you're adding diffusion via just an exact solution, exponential Gaussian type of thing. Is
Hmm.
that
Yeah.
correct?
Yes.
So you wouldn't get anything there, but I'm curious if what you're doing is able to pick up any shadows of these Gibbs artifacts, even though the MRIs may have been cleaned out. Would
Um,
just seem to be an amazing sensitivity test.
That is actually true, and it can actually be taken as a limitation. Initially, I put the point over here where we are actually using some metrics like FID, KID as to just understand the how good the images are. But then there is a very big gap where we are actually not able to capture the clinically plausible reasons, such as the reasons that you're mentioning. So that is one of our limitations. Yeah.
Okay. Thank you. Interesting work.
Thank you.
Beautiful. So let's thank again Abhinay for a great presentation. Thank you very much for going through the details of your work. Thank you for your time.
Thank you, Professor. Thank you for the opportunity. Yeah.